On and go. Right. What did we do last lecture, which happens to be yesterday? What did we do? What did we do? What about quantum physics one? Photoelectric effect. I show you why there is a need, like photoelectric experiment. Is an experiment that showed you why light cannot be described as just waves anymore. Shows that light might behave like a particle, behaves like a football, right? Kicking the electrons out, which also behaves like a particle, like another ball, basketball, soccer ball, whatever. All right. I showed you also the equation of Einstein's photoelectric effect. HF equals to half mv max squared plus phi, the work function. Okay. So today we are going to continue with that and look at some of the examples. Example number 2. A light bulb emits light of mean wavelength. So this is the wavelength. The light bulb is rated at 150 watts and 8% of the energy appears as light. How many photons are emitted by the lamp per second? Okay, carve up your answers a little bit, think. Don't just read the answers, think how you try to solve this question. Okay, so what do you see? What is one way to do it? If you know what Planck has got or what Einstein suggests, energy of a photon is E equals to hf. But you don't have the frequency. So you find it through the wavelength of the light. How do you find that? Using V equals to f lambda. But the velocity of light is a constant. That's why you have speed of light c. So c is the speed of light. Lambda is the wavelength of light. So hf becomes hc over lambda. Okay? Substitute in. This is mathematics, it's easy. Punch the calculator, you get your answer. This is the energy of one photon. Okay? Next, the lamp gives you 150 watts. What is that? That means 150 joules per second. 150 watts means 150 joules per second. But only 8% of it becomes light, and hence light energy. So 0.08, 8% of 150 watts gives you 12 joules. So if the total amount of energy is this, and then energy per photon is this, can you calculate the number of photons? Yes. Right, just take 12 divided by energy per photon, you get an answer of 10 to the power of 19 photons per second. So if you're looking at this, if you look at the LT, let's say each fluorescent lamp is exactly the same as this. Let's say. How many are there? Oh, you are being bathed in billions and billions and billions of photons per second. Do you feel anything? Nothing. Right? Because the photons are massless, so tiny, right? Doesn't really affect you. But this is the fact. This is the amount of photons per second. So just in one bright daylight, you have so many photons. Okay. Interesting story. I share with you a personal story. I just went shopping for light bulbs with my mom this weekend. Right. Right. So did I say this already? No. My mom went to the light bulb, and so she's choosing LED light bulbs. You all know why LED light bulbs are good, right? Better than normal light bulbs. Because for the same wattage, look at this. This lamp, only 8% of the energy is converted as light energy. Right? So in fact, on the LED label, right, the packaging, it says that a 15 watt LED lamp is as good as a 95 watt normal lamp. Right? A 15 watt LED light bulb is as good as a 95 watt normal light bulb incandescent that wastes a lot of energy in terms of heat. But the funny thing is this, my mom went to it and said, wow, this is a 15W light bulb. This is a 12W light bulb. This is the 10W. Then, as a physics teacher, right, you're like, no, it's watts. It's watts, mom. It's watts, right? But she's my mom, right? So she's always right. Okay, that was recorded. So sorry, mom. Example 3, right? Example 3. Example 3 is a lot harder, right? Let's take a look. Right, in the lecture until now, right, I showed you that for every electron comes out, it must have been a photon coming in. Correct? But does it mean that every photon coming in will kick out an electron? The answer is in fact no. In fact, in this example, in this question, we'll see actually how rare that is. Okay, so let's see. This is a real data, right? Very close to real data. So we use ultraviolet light of this wavelength and intensity of 210 watts per meter square. This shining on silver in the vacuum tube, right? And you have 12 mm of silver, right? The 12 mm square of area of silver is shined on. It's a very, very small area, right? Roughly 3 millimeter by 3 millimeter. So it's a very, very small area, roughly, right? Or 3 by 4 millimeter, roughly. A photocurrent of 4.8 times 10 to the power minus 10 ampere was collected. So here I want to pause and ask you. In the lecture, I presented to you what is a photo. Okay, let's try this first. Let's try this. I tried it in the previous lecture. I almost flipped in my chair and fell over. What is a photon? Don't need a definition. What is a photon? What do you feel? It's a light particle. It's a particle of light. Very good. This lecture very good. I feel warmed. Thank you. What is then a photoelectron? Let's see. This side very quiet. I sense the force here is not so strong. Last row. The 3 boys. One of you. What is a photoelectron? What is a photoelectron? Loudly, so that the whole lecturer can hear you. Shh. Sorry? Photons that carry an electric charge? Okay, no. So listen carefully. This is what can happen. No, it's not correct. Photons, right, are the particles of light. They carry no charge, and they have no mass. Okay, photons, P-H-O-T-O-N-S, belongs to light. Photoelectrons are electrons. They are emitted due to light shining on a metal. Okay, most of them got it. Right, so please make sure you all know. Okay? Photoelectrons, this side. Maybe I need to tilt my chair to this side. Sorry. And then you all can see that I'm facing you, then you're more serious, maybe. Right, so eyes on you. Right, so photocurrent. What do you think is a photocurrent then? Okay, so now central. You all heard what is a photoelectron. What do you think then is a photocurrent? Targeted. What's a photocurrent? Shh. Huh? It's a current due to due to light shining on the metal and producing electrons. It's the photocurrent. It's the current due to the electrons, due to the photoelectrons that are produced by light. Okay? Good. So now the question is this. A. Just finished. How was it? Wow, awesome. You get a round of applause. They won. Good job. Okay, never win also must good job. Okay. Now, what was the rate of incidence of photons on the silver? So now this question is quite similar to what we did before, right? The light bulb one on example 2. Let's see. You have the power, right, received by the surface. This is the intensity, 210. The area is 12 millimeters square, so it's 10 to the power 6. You put together, you get this amount of power, which means this amount of joules per second. You can then find the energy of a photon. This is quite similar to part 2. Sub it in, you find the energy of a photon is this value. So just like example 2, very, very similar. You can find the number of photons per second, and you find it to be 10 to the power 15. Ooh, slightly smaller than before. Okay? Any questions? But I want you to remember this number. Can you see this number? 10 to the power of 15, right? 10 to the power of 15. Moving on, what is the rate of emission of electrons? You have the current, right? You measure the current. So the current is the total number of charge per unit time. Total number of charge. And total number of charge is the number of electrons multiplied by the charge of the electron. You sub it in, you rearrange. You want to find the number of electrons per unit time is Ne over T. So rearrange, you find I over E, the current divided by the charge of the electron. You get this number, 10 to the power of 9. Okay? So roughly, what is the yield? That means for how many photons must you put in to get 1 electron? Roughly. It's not for sure, it's roughly. Well, let's take the difference, you get this value, quantum yield. If you flip this around, you take 1 over this value, it's roughly 1 in a million. There's a song, right? Then 1 in a million. Right, I was driving, then I was thinking, yeah, I must remind them the yield is about 1 in a million. Then next time the song come out, so it's stuck in my brain. Okay. Right, so really, every photoelectron that you see, every electron that you see is very, very lucky. Right? It is a result of chance, 1,000,000 to 1 chance. Huh? So 1 in a million. Every electron you see must have been due to at least 1,000,000 photons around that coming in. Okay? Right, next, example number 4. Example number 4 is for you to get a bit more comfortable with what is an EV. Right, in the previous section, I defined for you what is a 1 electron volt. So in this example, we are going to use EV to get a sense of things. So in work function of a metal, I can give it to you in terms of joules. I could give it to you in terms of EV. Both are units of energy. Okay, so you must be comfortable with both of them. Okay, so the threshold frequency and wavelength, let's use the equation. At threshold frequency, the energy of incident photon HF naught is equal to the work function of the metal. So basically this part. Rearrange, you get this answer. So the difficulty here is knowing how to convert EV to joules. Right, you must take joules over Planck's constant. Right, so can you annotate in the working, can you write the top part, 1.9 times 1.6 times 10 to the power minus 19. This whole thing is so that you can convert EV to joules or joules. Okay? but they don't want the threshold, or they want both the threshold frequency and the threshold wavelength. Wavelength easy. Speed of light v equals f lambda. Rearrange, you get this answer, 6.5 10 to the power minus 7. Okay? Next, they say what is the maximum speed which electrons will be ejected if violet light of 405 nanometer is shone on the surface. So make sense or not? Listen, for frequency, you have a threshold frequency, you have a minimum frequency. The higher the frequency, the faster speed of electron. But for wavelength, the shorter the better. Correct? So the light that you shine is 405, is shorter than 650. Correct? So you should expect your electrons to come up with certain energy. So how do you do that? Use the equation again. HF becomes Hc over lambda. This is work function. This is the half mv squared. Substitute everything in. Boom, 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 boom. You realize you have everything except Vmax. Solve. Easy peasy. Okay? Questions? At this point, any questions? Okay. So, what have we done until this point? We have familiarized ourselves with this Einstein's equation, right, for photoelectric effect. But you know that this equation is only for one particular case, correct? It's when the velocity is maximum, which means the electron that I'm measuring is the electron that has escaped from the surface of the metal. What about the rest of the electrons? What about the rest of the electrons? So the next part, 3.2, we are going to investigate that. Okay? We are going to investigate that. So these are some of the guiding questions. Can you write it down at the top? How do you get your IV graph? How do you get your stopping potential versus frequency graph? When the intensity and frequency of light is changed, how do these two graphs change? When the metal is changed, how do these two graphs change? Right? So the next part is about graphing, right? How do you know what happens? So it's very applied, right? It's very applied. If I change this variable, what happens? If I change this variable, what happens? Okay? So again, how does the IV graph change? How does the stopping potential versus frequency change? And when I change the intensity, frequency, and metal, how do these two graphs change? Okay? So first up, we have the IV graphs. Let's start. Last lesson, I explained to you this setup, okay? But this setup is not very useful to explain IV graph. I need to make some changes to it. If you shine red light, nothing comes out because it's not yet the threshold frequency. You shine purple light, electron comes out, current flows. Okay? This is the general idea, but I need to make some changes to go into further detail. I show you this. What have I done? From this page to this page, I have brought down the potential divider. I've enlarged the Jockey region, right? So watch. Here, I don't let the Jockey touch the potential divider. What happens? It means that now your E and your C have the same potential because they are joined to the same line. Can you see? This part of the battery comes here. It's joined to both E, goes through V, and also joined to C. So they are the same potential. They are both in the same, in case, neutral. We can call it neutral. Okay. So now let's look at the life of 3 electrons: the slow, the medium, and the fastest. What will happen? When you shine light, they'll all come out, but they'll come out with different speed. The slow one, okay. The medium one, faster. The fastest one, boom. Once they reach this side becomes a bit more positive. The electron will flow through the emitter, through the voltmeter and back to E. Hence, you detect a current flow. Okay? Once you do that, you can say mark a cross on your IV graph and say, okay, I have a certain current. Okay? Next, watch. What's the change? I now place the jockey onto the potential divider or onto the wire. What happens? The E side becomes a bit negative. The C side becomes a bit more positive. Can you see? The negative end is connected to E. The positive end is connected to the jockey. It's a bit more positive than your E, so the C side becomes positive. What happens? The electrons are all attracted to the collector. So the slow one goes and touch, the medium one goes and touch, the faster one goes and touch. All of them go. So whatever you have measured before, in the current, is measured again. Am I right? All follow me? Nod your head vigorously. Right? Okay. So I repeat again. Now I maximize the voltage. What will happen? Actually, it's the same thing. Slow one touch, medium one touch, fastest one also touch. Right? So you can make a series of, and you see this. The current stays the same throughout. This is also what you call the saturation current. If you don't change the intensity of the light, that means the number of torchlight shining on the metal, the intensity stays the same. Right? And knowing just now the quantum U, right? For every million photons, roughly 1 electron has come out. Since you don't change the number of photons coming in, the number of electrons coming out will not change. And since all of them are attracted to the collector, the current stays the same throughout. Okay, this part no problem. Good. Now watch what happens. Watch the screen carefully. Oh, wait, don't like that. So you eventually get this, okay? This is the summary. Okay? Now watch what happens. Watch, ready, go. What happens? I flip the battery. The collector side now becomes negative, and the emitter side now becomes positive. What happens? There's still a current flow, right? But now we're going to do something different. Watch. I flip the battery. This is initially. I now flip the battery. You can see. Watch the battery here. I flip it to the other side. Now, the emitter side now becomes positive. The collector side now becomes negative. So what happens? For every electron that's coming out, what force does it feel? It feels a force to the left. Okay, so let's see. The slow one, it comes out. Oh, okay. The medium one, it comes out, it feels a force, but it can still have enough energy to reach the other side. The faster one definitely can. But the slow one, it tries to go. Come back. Cannot reach. It tries to go, but it cannot reach. Now, instead of 3 electrons, you only measure 2. Your net current must have decreased. Agree? I do it again. I now shift my jockey to this point. Can you see? The potential will now be higher. It's more positive at the E and more negative at C. The slow one, come back. The medium one, cannot. The fast one, okay, touch. So you still got some current. Can or not? Can? It's a struggle. It's a struggle, but I still reach. I move my jockey again. I move to this point where this happens. The medium one and the slow one all cannot touch. But the fastest one, look, it goes, yes, no. Right? By a hair's width, just barely, it cannot touch. Your current now becomes 0. Okay? And this value of the potential, this V, is called the stopping potential. Okay? This V is called the stopping potential. Can? Understand very clearly? Good. Moving on. right? And how come there's a stopping potential? In fact, the concept comes from electric fields. It's a conversion of energy, right? To reach this plate, you must lose KE and gain EPE. But if the potential is so different, so large, that the potential energy is so large that even if you lose all your KE, you still cannot gain the same EPE, you will have what you call a stopping potential, because the electrons will never touch the collector. Okay? And this is a very key equation to know, right? How the kinetic energy is linked to the electrical potential energy, EVS. EVS. All right? So with this, we can then change this equation. I presented to you this Einstein's photoelectric effect. But seriously, I ask you, can you visibly look and find the speed of an electron? You can see the speed of a car, but you cannot see the speed of an electron. Correct? So how? How do you then measure the energy of the electron? You have no choice but to measure the stopping potential. Using potential difference, the voltmeter allows you, this Vs allows you to measure half mv squared, half mv max squared. You understand? So this is why we need to have a Vs, EVS. Right? So by we rearrange, we get this equation. Next is some mathematics. Once we have this, we rearrange some more. We get this. We get Vs on the y-axis, F in the x-axis, H over E as the gradient, and phi over E as the y-intercept. This allows us to draw this graph. Okay? This allows us to draw this graph. So the gradient is H over E, and the y-intercept is phi, work function of the metal, over E. Okay? So one of the peculiarities of this graph, please note it down, is that the gradient is always constant. Planck constant is a constant, never change. E, the charge of the electron, will also never change. So for whichever Vs over F graph, the gradients will always be the same. What changes is only the y or x-intercept. And that is dependent on the metal, on the work function of the metal. Okay? But how do you actually draw this graph? Okay? So I show you. You start off with a red colored light. A red colored light has low frequency. And to stop, you bring the current to zero, you find a certain stopping potential. So at that frequency, you have a certain stopping potential. I now use green color light. Green color, frequency is higher. Hence, the stopping potential must be higher. I make one X, I make another X. I use blue color light, violet light. Frequency is even higher, stopping potential is even higher. That is how I get the Vs versus F graph. Okay, once I have the X's, I draw a line, that's how I get it. And with this, I draw the line back down, I can then decipher what is the threshold frequency. Here, the point where it joins the frequency line is the threshold frequency. Okay? So if we plot this again, we have this. So now what if we change the metals, right? Remember one of the questions I have in the guiding question is, what if we change the metals? If we change the metals, this is what we get. Okay? These are not any random metals, but they are specific metals. This is cesium, potassium, and beryllium. Of these three metals, do you all know in chem which metal is the most reactive? It is a cesium, right? Cesium. In fact, cesium, if you shine visible light at it, it will start to emit electrons already. Can you see? That's why the F0, the threshold frequency is the smallest. Potassium is next is beryllium. Okay? So if you draw different metals, you notice that the gradients are all the same. What changes is just a shifting of the graph to the right or to the left. And ABC are the threshold frequencies due to the metals having different work function. Okay? So below this graph, I want you to write the work function of CS, work function of K, and work function of BE. Which one is the largest? Which one is the smallest? Okay? Take 30 seconds to write. Should be quite easy. Go. Okay, good. Right. So this is the IV graph again for different frequencies of light. This is for the graph on page 10, but notice that it's slightly different from your graph. Your one gives lambda 1, lambda 2, lambda 3. But you get the same idea. If I change the frequency of light, I must have changed the wavelength of light because speed of light is always the same. Okay. Here, notice something. Constant intensity in Cambridge sense, generally, it's not always true, generally means same rate of photon arrival. But intensity, if you think about it, is actually power per unit area. So, if you have constant intensity, it doesn't mean constant rate of photons. It only means constant rate of photons if the frequency of light stays the same. Constant intensity means constant rate of photons if the frequency stays the same. Okay. But anyway, most of the time that is a question, it will be true. With a constant rate of photons, you have a constant rate of electrons, hence the current stays the same. For the same metal, you have the same work function. If you then vary the frequency of light, here, when you vary the frequency of light, you are making something very constant. Here, you must be very careful. Can you indicate that you are fixing, for sure, the rate of arrival of photons? That means if you change the frequency, but you very mindfully keep the rate of photons the same, then you can get this graph. Okay? Here, the stronger criteria is you keep the rate of photon arrival the same, then you can get this graph. Okay? Because keeping intensity the same while changing frequency, the number of photons must have changed. I'll go and think about that. Right. Let me now show you a demo. FET. These are the guys from FET who have brought you this very nice demo. I did all the... You mean I've been presenting with this side? Nothing. Why nobody tell me? Oh, it's down. Okay. Oops. Yeah, sorry, I didn't have eyes on the back of my head. I didn't check. Right, let's look at the FET diagram. Yeah, the FET stimulation. So let's see what we can do. Just now we talked about the current voltage graph. So let's not look at the graph. Let's just look at this. I shine infrared light. Infrared, the frequency high or low? Very low frequency, right? Wavelength is very long, frequency is very low. I increase the intensity. I make the light bulb stronger, stronger, stronger. Right? Got photons come out. Got photons come out. Have. Photons is the light. So the stronger the light, the stronger the number of photons, the larger number of photons. But got electrons not? No electrons. No electrons. So let me put this at 50. I bring down the wavelength. That means frequency is increasing, frequency is increasing, frequency is increasing. Oh, the electrons are now being emitted. Of course, they are moving a lot faster than this. This is a simulation. And then they touch. Then got current already. Okay, very small, too small already. Maybe I increase the intensity. I increase intensity, more electrons should come out. Or still not enough. Too small. Okay? But you can see, so now let me increase the frequency some more. Now let's see the range of velocities of the electron. Let's shift it to around ultraviolet. Oh, now you see, got difference not? You have a fast one, and you have this one. Or this one. Huh? Everybody, hey, we're late for class already, hey, hurry up, hey. Hey, never mind, hey, never mind, hey, brother, hey. The class finished already, still walking, hey. This kind of student. Now see what happens. Let's look at the IV graph. Look at the battery. This is neutral. I'm going to shift it more to this side, to the right a little bit. This side now becomes more positive. Or maybe let me shift this down further. Like that. Okay. So to a very, very ultraviolet, 243 around there. Just make it smaller. So as I shift this battery to the right, what happens? Look at the graph. Follow the graph. I make it more and more positive. Can you see that current stays the same? Current stays the same. Why? A lot of students asking me, hey, Mr. Ho, no, if you make it more positive, the electrons are moving faster, shouldn't the rate of arrival of electrons be faster? But no, look, you are producing 10 electrons per second. No matter how fast they are moving, you will only receive 10 electrons per second. Correct or not? A lot of students in the previous lecture came down and asked me. I'm producing 10 electrons. I let them move very, very, very slowly, but only 10 will still, but 10 of them will still reach here if they are, all of them will reach here. I make it very fast, also 10 will reach here per second, so the current stays the same throughout, regardless of how fast they are moving. All the way, 8 volts, still the same. The current stays the same. It's dependent on the number of electrons produced per second. Now let's look at the other side. Now let me flip it around. Go down to 0. I go down a little bit. Oh, you see this electron? Ayo, come out, go back. Oh, rejected. Got any more rejected? Wait, this one, almost. Oh. Your current will drop. Let's make it more drastic. 0.6. Now you see a lot more electrons being repelled back. So sad. Almost reached the other shore already. Right? Almost. It's like NAFA need one more push-up. So sad. Let's do it some more. Sorry, I touched a sore point for many of you. Sorry. I also know I do army, so you know. Okay. Do this. See, even more electrons are rejected. I do it some more. See, getting closer. Very close already, right? But still there'll be some electrons that can touch. See? Wow, just nice. Let's do it some more. Wow, you see? Can you see? Oh, cannot reach. Cannot reach. Huh? Stopping potential, how much? 2.8. Okay? Stopping potential, 2.8. Okay? Now, let's change. Let's look at the electron energy versus frequency. Right? This is the electron energy stopping potential versus frequency graph. If I change the frequency, the stopping potential will change. Okay, so here is, I will change this. Look at the graph, it changes. You see? The higher, the lower the wavelength, which is the higher the frequency, the faster the electrons are coming out. This one don't even come out. So here, some are coming out, but the lower the stopping potential. So around here, it should work. Around here maybe, it will work. So 1.2 corresponds to this frequency. I make it lower frequency, the electrons will have more energy. So this potential will not be able to stop it. So I need to lower some. So this battery tells you your EV. Right, if you look, okay, let me shift. I shift to around where the line is around 4. Okay, look. At this frequency, roughly here, at this frequency, the electron volts of the electron is around 4, which means that if I shift this battery to 4, almost all the electrons will not touch. Let's try. Can you see? At 4, current became 0, all the electrons cannot touch. Okay? So go back and play with this applet a little bit. One more. Maybe I just open up. But now look at the middle graph. Current versus light intensity. Okay? Shift this to 0. If I change the light intensity, watch the green graph. I change the light intensity, if light intensity is 0, no current. Some intensity, some current, some intensity, some current, some intensity. Okay? So the middle graph is a graph that both quantum and classical wave theories, they concur, they agree. The one on top, the one below, right, they don't. It's only by quantum theories that they get this. Okay? Good. So what have I done with you today? Okay? Oh wait, yeah. So let me go back to the slide. So what have I done with you? I've done this slide. Show that for the same metal, same wavelength, when you change the intensity of light, you change the number of photons, you change the current, but the stopping potential stays the same. That is your graph number 2 on page 10. If you twice the intensity, you twice the rate of photons. If the wavelength is the same, you twice the current. Easy peasy. I also showed you the current versus intensity graph in the applet just now. The more photons you have arriving due to the intensity increasing, the more current you have emitted due to the electrons being generated. Hence, you have a greater current. Okay? And this is a conclusion, right? Very interesting. With quantum theory, we have shown that light have particle-like properties. But does it mean that it only has particle-like properties? The answer is no. Light actually have a wave-particle duality. And later in quantum 2, next lecture is still ours. We're going to do some tutorial questions, so go and prepare. Right? Next lecture, next week, we're going to do some tutorials. But it shows here that light has a wave-particle duality. And later on in quantum 2, you will learn that electrons also have a wave quality. Electrons, which is a particle, has a wave quality. Okay, wait, don't go. So I also want to show you this. A lot of students ask me, in the past, I shared with my students I used to work in a quantum research lab. Yeah, I used to work in Center of Quantum Technology. My lab, my prof is German, he's here. My second prof is Spanish. My co-workers are Russians and Germans and Indonesians and Malaysians. And basically, I'm the only Singaporean. Okay? So I want to share with you what I've done. So you say, a lot of people say, wow, research very boring. Sometimes. Okay? I'll show you the cool one. So my prof is really cool. My profs are really cool. Right? This is what we did. Okay, please look. So we went on a quantum road trip. We went to Las Vegas for a conference. Right? We were showing them what the cool stuff that we've done. Right? So we went for a road trip. We went to do a real experiment over the Grand Canyon. So which you cannot imagine it right now as a student. Like, go to Grand Canyon and do experiment, mind blown, right? So sorry. Don't burn your eyes, close your eyes, okay? That was me when I was younger and kiki. I'm still kiki, but more handsome. So we are driving, we saw some cool stuff along the way. What were we doing? So what was I doing during that period of time? I was doing what you call quantum cryptography. I was doing a research on quantum physics and cryptography. All right, I was doing quantum physics and cryptography, which is super tough. Right, so I'm on the receiving side. Look at how big the telescope is. What we are doing is that we are taking two lasers 3 kilometers apart and try to align it. So I ask you, if you take a handheld laser, a green pointer, and you shine 3 kilometers, can you make sure it goes exactly where you want it to go? It's not that easy, right? There's a lot of optics involved. So it's a quantum research, but it's also, you need a lot of good optics skills, a lot of optics physics there. So if you shine a green laser 3 kilometers away, do you know how big that spot is? When you shine a laser here to the room, the spot is the same size, correct? But you shine 3 kilometers, you know how big the spot is? It's the size of this room. Yeah, it's the size of this room, right? So that's what we did. We shine a green laser to align the two telescopes. Then we use an infrared to send the secret laser. Infrared man cannot see. The green one, everybody can say, hey, you're shining a laser, and then I can attack you. Because cryptography is all secret. It's all about sending secret messages. So you send an infrared beam, cannot see, and you have to change the beam such that the beam doesn't become big. It becomes tiny all the way across 3 kilometers. It's not easy. This guy is Matt Peloso. We were both suffering in the lab. We were both our master student. He's now the CEO of a solar company, about $100+ million. Right? Because science brings you everywhere, right? And I have you all. I'm fulfilled. Right? So this is the setup, right? What is this setup? What is this setup? This is a setup that does quantum entanglement. This is in fact something that Einstein don't believe in. Einstein is a giant, right? This whole chapter is about Einstein, right? It's about what we have done. Einstein believed these things, and we have photoelectric effect. He earned a Nobel Prize for it. But Einstein also believed in some other things that was not correct. Right? Einstein believed some other things that's not correct. It's called entanglement. He doesn't believe in entanglement. Right? He doesn't believe in entanglement. And in this project that we are doing, right, we are proving him wrong about 6,000 times a second. We are using a laser to show that he's wrong 6,000. And now this setup, this is 8 to 10 years ago. My co-workers have now sent this on a satellite to space. Right? The setup, you see how big it was? It is now smaller than my water bottle. It's now smaller than water. This is the initial stage where we work on and really try to push the frontier of science at that time. Okay, so what did you also do? So show you this. So it wasn't it was fun, right? It was fun. So this is what we were doing. I was trying to align the angle of the receiving telescope. So this is where you are. So we are really literally at the edge of the canyon. Any wind, anything. Why you all see me and you all laugh? No, I don't. Okay, never mind. Please tell me later on. Okay. You all don't believe, you all don't imagine, right? But I also don't imagine that when I was a student, why you can imagine you take a laser, go to Grand Canyon and go and beam and do quantum stuff there. Cannot believe one, but in 6 to 10 years, many of you will be doing things that you all cannot imagine now. Night 3. So night 3, we're there. So this is a telescope. You can see it. This is my German colleague who wanted to place it right at the edge here. Gonna scolded. Oops, he's hearing this. So then we are aligning. So we are showing you the scenery lah. So this is where we are. We are beaming it to the other side, and we are trying to send an encrypted message across. So we are on the other side. And I show you the beam. Now we are aligning it. So you see vernier caliper. You all learn vernier caliper, right? Must be very specific one. Okay. Then we try to align it. Aim it very carefully. It's like last time, right? When you're on a boat. Oh, yes, I see a ship. Then but now it's more specific. It's photons. We are dealing with photons. We are trying to catch a photon. Imagine this: 10 to the power of 19 photons, right? but it's trying to catch one photon. So this is a green laser. Can you see how big it is? The green laser is affecting everything else here becoming green. Can you see? It's all green here. This is the green laser, making it all green. Huh? Yeah, so anyway, the whole, if you all want to know more, right, to know about what research is like, you want to pursue a career in research, can come and ask me. If you want to know about quantum research, you can also come and ask me, okay? With that, I'll see you next lesson. Bring your tutorials, do them. Thank you very much. Bye-bye.